Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using KNIME. In this chapter we'll be covering logistical regression, different from multiple regression in that the dependent variable is going to be a categorical variable. In statistics, logistics regression is a model where the dependent variable, as I said, is categorical. In other words, it only has two variable solutions, pass, fail, win, lose, on, off, true, false. That type of categorical variable doesn't lend itself well to the linear regression models that we've been using. And so we'll have to do something slightly different. But first, maybe we should explain when we use regression and why it doesn't work with a categorical variable. Recall that there are three conditions that are required to use simple linear regression. There has to be one independent variable and one dependent variable. All the variables must be on an interval or ratio scale, and the correlation between the variables must be linear, not collinear. When we're dealing with categorical variables, it's number 2 that is not true. Let's look at an example. When using income data as a predictor variable, we're going to try and determine the probability of an individual purchasing a specific product. Why don't we use linear regression? We have a continuous predictor variable, income, that is on a ratio scale, but we have a binomial categorical outcome variable, in other words, buy versus don't buy, that's on a nominal scale. And this is going to create a few issues for us. First off, a binomial outcome inherently has a lower and upper bound of 0 and 100%. Any probability outcome above these doesn't make any sense. For example, you can't be 135% chance of someone buying a product. It doesn't make any sense to exclude linear outcomes above or below these boundaries because any of these individual income levels could still purchase a product, as you can see in the sample chart below. What we need is a regression solution that will provide us with two things. The first, a continuous outcome, so all income levels will be addressed, and the outcomes that will respect the 0% and 100% boundaries that wouldn't normally be included in a regression model. How does logistics regression solve these two problems? Well, regression equation will yield a continuous outcome in logarithmic units instead of the unit of measure that you were provided with. So we will then convert the logarithmic units to probabilities of buying, which will still keep us between 0 and 100% bounds. The easiest way to do this is to actually look at this as an example. So let's do that. Now the only problem if I do this in KNIME is it's going to hide all of the individual operations behind the scenes so you won't see it. So let's first take a look at how we would do this in Excel so you can understand the mathematics behind it. And then we'll show you how we do it in KNIME where all of these operations are hidden from you. Alright, here I've built up a sample Excel spreadsheet. And I've got a purchase indicator, which is a 0 or 1, that shows 0 is they didn't purchase and 1 is they did purchase. And then their income in thousands. And then for my formula, I'm going to use a y-intercept of 1 for now and an income coefficient of 0. I don't know what the values are here. And at this point, I'm going to let the Excel equation solver solve for that equation. So I'm not going to try and worry about that for right now. So the first thing I want to do is convert my number to logarithmic units. And I've done so using the standard linear equation. So the y-intercept, so A2, plus the B2 times B5. So the income coefficient right there times the value. So that's the logarithmic units. Now I can compute the probability, the raw probability, in this case specifically the probability of a person buying or not. And I'm doing that by using the exponent function in Excel of the D5 column. And then finally I can produce the number that we're actually looking for, the actual probability of buying as a percentage. So E5 divided by 1 plus E5 gives me a percentage value. Now that we have the continuous outcome that actually respects the 0% to 100% boundaries, now we need the equation that best fits the graph. The linear equations we've used in the past have used the least squared methods. In logistic regression, it's the maximum likelihood. And the first thing we need to do is set up the column with the probability of each buyer. So since not everyone will buy, if the row is a buy, what we want to do is use the probability of buying, meaning if this is a 1, use the probability of buying. Otherwise, we want to use, it's the probability of buying is 1 minus the probability of buying. And if the probability of buying is 73%, the probability of not buying is 27%. So I'm going to do this based on action, and we're going to use an if statement in Excel to say if A5 is 1, use F5, otherwise use 1 minus F5. And that's now my computation based on. Now the last thing we need to do is repeat all of this work. So we've got this all for the first line. So let's go ahead and copy this, and we'll scroll down and paste it all in here. So now I've got the same values. And again, don't be concerned that the same values are all here. This is what we need to do. So the last thing we want to do is we're going to compute the probability and the natural logarithm. All right. The next thing we need to do is multiply all of the individual actions against each other. So basically we need to compute the product of this number. So what I've done, and this is the product of probabilities. So what I've done here is set it equal to the product of the columns from G5 all the way down through G40. And then finally, we take the natural log of the product, which in this case, I'm going to use the natural log function of what is in G42. This is a number we're going to use to find the best fit equation. We want to get this number as close to 0 as possible. And for this, we're going to use the Excel problem solver. All right. Now we want to solve for this by going to the Data tab, and there is an Excel add-on tool called Solver. And I'm going to, if you've installed that add-on, if not, you can literally search for Solver up here in the search bar and it'll add it for you. But I'm going to add the solver here, and here's what I want to do. I want to solve for, the objective is the cell G44, getting that to a max value of 0. That's what we're shooting for. And I'm going to do it by changing the variables in cells A2 and B2, the coefficients and the y-intercept. And make sure that you've unchecked make unconstrained variables non-negative. And then finally, using a nonlinear formula is how we're going to solve this equation. So when I click OK to solve, it tells me that it's been able to, after 5 iterations, it came up with the minimum value for it. And I'm going to go ahead and keep these solver solutions and click OK. So as I go back up to home, it's now computed the y-intercept to be negative 9.17952, and the income coefficient is 0.09. And you now know the predictive formula that you're going to use is negative 9.17 plus 0.09 times the income. All right. Let's go ahead now. That was a lot of work. Let's go ahead and do this in 9, where all of this work is going to be hidden to your, hopefully, joy. And let's see if 9 comes up with the same values. All right. I've mocked up the same data using a table creator in 9. And I can look at the data now. So I've essentially created a string column with a yes-no indicator and the same income levels. And so all of this data is the same other than changing 1, 0 to yes, no. It's the exact same data. Now, what I want to do in the node repository is, instead of the regression learner and predictor, we're going to use the logistics regression learner and the predictor. And otherwise, you'll notice many of the same concepts are held to be true. So let's go ahead and configure the logistics learner. I'm trying to guess or understand yes categories, basically people who are going to purchase. And I'm not using stochastic gradient averaging. I'm going to use least squares averaging, and then income levels of 1,000. And I'm going to go ahead and execute this. And now, let's go ahead and take a look at the coefficients for this. Okay? Now, KNIME will turn the signs around. This is just a product of how KNIME works. It's not going to change your scores, and it's not going to change your model and how it works and the slope of the line, etc. But what I can see is my y-intercept is 9.183, and the coefficient is negative 0.092. Now let me pull this back up, and you can see what we had in Excel, and pull this up so I can look at them together. Okay. My coefficient of 0.09223, it's got 0.092, and again, it switches the signs around. That's okay. And then the y-intercept, instead of 9.179, it's 9.183. Slightly different, but the benefit, of course, here of what you're seeing is that KNIME was able to do all this without you having to understand all of the mathematics behind what just happened. Now in my predictor, and I run the data through the predictor to see what it comes up with, I'll be able to look through and see this was the actual, did they purchase or not, and this is what the prediction was going to be. Now, there's no residuals like there would be in a linear regression formula, but what I can do in the node repository is add a scorer node to this. And within the scorer node, okay, the first column I want to compare against is predicted purchase against the actual purchase. And then tell me what they score. Now, I can view the confusion matrix, and what I show you is this. We're going to talk about confusion matrix and the sensitivity and specificity and accuracy values in the next chapters when we get to talking about building decision trees. So for now, just go with me and relax and understand that right now what they're trying to tell you in a confusion matrix is the number of times that it guessed no and the actual value was no. So 13 times it guessed no and it was no. 3 times it guessed no and it was actually yes. 3 times it guessed, 5 times it guessed yes and it was no. 15 times it guessed yes and it was yes. So this is what will yield our accuracy statistics and our R-squared value. The accuracy statistics, again, we're going to learn all about the previous element we just knew, and we'll go through all of that. But what I'm looking at right now is the overall accuracy of this model is 77%. In essence, that's my R-squared value. We'll talk, like I said, about how to interpret all of this information because it's an entire chapter by itself. We will talk about that in a later section. That completes this chapter of the class. Feel free to move on to the next chapter.